Welcome to WikiPodcast. You might think waves just sort of pass right through each other,
Right.
like unaffected.
Yeah, like ships in the night, as they say.
Exactly. But what if when they met, they actually combined, did something totally different? Like,
Oh.
what if they could cancel each other out, just vanish for a moment, or maybe become way stronger?
Or even bend around corners. That definitely challenges our everyday intuition.
It really does. But it's not science fiction, is it?
Not at all. It's fundamental physics.
Hmm.
How waves actually behave.
Right. So this deep dive is all about these, well, kind of mind-bending behaviors, specifically interference and diffraction, core ideas in wave physics.
Especially for things like sound and light.
Yeah, and we've looked at a whole bunch of material on this, and our mission really is to pull out the key insights for you, how these interactions create amazing patterns and, enable some cool technologies.
Okay, so where do we start?
Well, the foundation for all of this is the idea that when waves of the same type arrive at the same spot at the same time.
They don't ignore each other.
Exactly. They combine, they influence each other.
And there's a principle for that, right?
Superposition.
Superposition.
Right.
And it's actually simpler than it sounds. Basically, the resulting wave's displacement, or amplitude, you can think of it like its height, is just the sum of the individual wave amplitudes right at that point, at that moment.
So they literally just add up, like mathematically.
Pretty much. A vector sum, technically.
Yeah.
But yeah, they add, if one wave is trying to push things up by 1 unit and another wave arrives at the same spot trying to push up by 1 unit.
Then the result is 2 units up.
Exactly. They merge at that overlap point.
Okay, that's the core. And this simple addition leads to these dramatic effects you mentioned.
Absolutely. It leads to the 2 main outcomes.
Mm.
Constructive interference and destructive interference.
Constructive and destructive. Okay.
And which one you get depends entirely on their relative timing. We call it their phase when they meet.
Right. So constructive is when they're like perfectly in sync.
In phase.
Yeah.
Exactly. A peak meets a peak. Or, a trough meets a trough. They're doing the same thing at the same time.
And their amplitudes add.
They do. Crest meets crest, you get a bigger crest.
Yeah.
The resulting wave has a larger amplitude, more intense.
Like pushing a swing at just the right moment.
Perfect analogy. 2 pushes in sync make it go higher.
Okay, so that's constructive. What about destructive? That sounds more dramatic.
It can be. Destructive interference happens when the waves are out of phase. The classic case is when a peak from one wave meets a trough from the other.
So they're doing opposite things at the same point.
Exactly. And in that case, their amplitudes subtract. One's pushing up, the other's pulling down.
So the result is small.
Smaller amplitude, yes. And here's the really wild part. If the waves have the same initial amplitude and are perfectly out of phase, like exactly half a cycle apart.
They cancel out.
They can, yeah.
Right.
At that specific spot, the amplitude becomes 0. Total cancellation.
Wow. Like pushing a swing equally hard in opposite directions.
It just stops.
Okay, the material used the analogy of dropping 2 stones in a pond.
Ah, yes. A classic. You see the ripples spread out.
And where they overlap, you see spots where the water is really high, really choppy.
That's constructive interference. Crests adding to crests.
But then, crucially, you also see these other spots, almost like lines radiating out where the water is still, really calm.
Exactly. Those are the points of destructive interference. A crest from one ripple meets a trough from the other, and they cancel out the water's movement right there.
Okay, constructive makes intuitive sense, things add up. But destructive, if the waves cancel, the water's still. Where did the energy go? Did it just disappear?
That's a really common question.
Yeah.
And no, the energy isn't destroyed. Physics is big on energy conservation.
Right, okay.
It's redistributed. The energy that would have been in those quiet, destructive spots has essentially been shifted over to the constructive spots, making them even stronger.
So the total energy in the whole pattern stays the same. It just gets concentrated in the high spots.
Exactly. Think about the pond waves again eventually. All that energy from both the high spots and the canceled spots reaches the edge and gets absorbed. None of it just vanished.
That makes sense. It's redistributed.
Oh,
Okay, and this isn't just water waves, right? This happens across the board.
absolutely. The sources are clear on this. Light waves, radio waves, sound waves, acoustic waves.
So the sounds we hear can interfere.
Definitely. Even gravity waves and, fascinatingly, matter waves too.
Matter waves, we'll have to come back to that one.
We will. And even electrical signals in circuits. Interference is everywhere.
Let's zoom in on light, though, because like you said, we don't see the wave itself, we just see brightness.
Right. That makes optical interference a bit different to visualize. We can't directly observe the oscillating electric and magnetic fields.
So what do we observe?
We observe the intensity, the brightness. And intensity for light is proportional to the square of the wave's amplitude.
Okay, intensity equals amplitude squared, basically.
Loosely speaking, yes. So when two light waves interfere, the intensity you see isn't simply intensity 1 plus intensity 2.
There's more to it.
There is. The formula includes an extra bit, the interference term. And this term depends directly on the phase difference between the two waves.
Ah, so that's how the phase difference becomes visible.
Exactly. When the waves are in phase, constructively interfering, that interference term adds to the brightness. You get a bright spot, a maximum.
And when they're out of phase, destructive.
The interference term subtracts, reducing the intensity. You get a dim spot, or if the waves had equal intensity to start with, a completely dark spot, a minimum.
So those patterns of bright and dark bands you see in experiments,
Like Young's double slit.
they're literally a map of the phase differences between the light waves arriving at different points on the screen.
Precisely. It visualizes the wave interaction.
Now, you mentioned getting stable patterns. The material talks about needing the light to be coherent. What does that actually mean?
Coherence is key for seeing stable interference with light. It basically means the waves maintain a constant, predictable phase relationship with each other over time and space.
So they can't just be randomly fluctuating.
Right. Generally, they need to come from the same original source, or sources that are very, very closely related in frequency. If the phase relationship is random, the interference pattern flickers too fast for us to see, and it all just averages out to uniform illumination.
And polarization matters too.
Classically, yes, they need the same polarization state to interfere fully.
Okay, so a regular light bulb, like an incandescent bulb, that's not coherent.
Not really, no. It's emitting light waves of many different frequencies, starting at different times, different phases. It's a jumble.
Which is why seeing light interference used to be hard. You needed special lamps.
Exactly. Historically, physicists use things like sodium lamps or mercury vapor lamps, often with filters, because they emit light in narrower frequency bands. That gives you enough coherence to see fringes, although they might be faint.
But then, lasers.
Lasers changed everything for interference demonstrations. They produce light that's much closer to being monochromatic, a single frequency, and highly coherent.
So the phase relationship is very stable.
Very stable. You split a laser beam, send the two parts on different paths, and recombine them, and you get beautiful, high-contrast interference patterns really easily.
Can you see interference with, say, white light? Which is definitely not monochromatic.
You can, actually. But the pattern is different. Instead of just bright and dark bands, you get colored fringes.
Because different colors interfere differently.
Yes, each color, wavelength, interferes constructively and destructively at slightly different positions based on the path difference. The cool thing about white light fringes is that the central fringe, where the path difference is 0 for all colors, is white. It helps identify that 0 point.
Interesting. Okay, so how do you actually make light interfere? You mentioned splitting the beam.
Right, you need to take light from a source, divide it into two waves somehow, let them travel potentially different paths, and then bring them back together to overlap.
And there are two main ways to do the dividing.
The material highlights two main categories. First is amplitude division.
Amplitude division. Splitting the brightness.
Sort of. You use something like a beam splitter. Think of a half-silvered mirror. It reflects some light and transmits the rest. So one beam is split into two beams, each with roughly half the original amplitude, going different ways.
What kind of instruments use that?
Things like the Michelson interferometer, which was crucial for that ether drift experiment, or the Mach-Zehnder interferometer. They're common in optics labs.
Okay. And the second way?
Is wavefront division. Here, you're not splitting the beam's intensity with a mirror. You're dividing the wave itself spatially.
Like, oh.
The most famous example is Young's double slit experiment. You let a wavefront hit a barrier with two narrow, closely spaced slits. Each slit acts like a new source, letting a portion of the wavefront pass through.
Ah, so you're dividing the front of the wave into two parts.
Exactly. Lloyd's mirror is another example where part of the wavefront reflects off a mirror and interferes with the part that travels directly.
Now, you mentioned Young's double slit. That brings up the other big topic, diffraction. The intro mentioned waves bending around corners. That's diffraction, isn't it?
It is, and it's really important to understand that diffraction and interference are, well, deeply interconnected. They aren't really separate things happening.
Okay, how so?
Diffraction is the phenomenon where waves spread out when they encounter an obstacle or pass through an opening. Like if a wave hits a single slit, it doesn't just travel in a straight line through the opening, it fans out on the other side.
It bends.
It bends or spreads. Now, think about the double slit again. Diffraction is what causes the wave passing through each slit to spread out.
So the spreading allows the waves from the two different slits to overlap in the region behind the barrier.
Precisely. If the waves didn't spread out due to diffraction, they would just continue as two narrow beams, and they wouldn't overlap much, so you wouldn't see much interference. Diffraction creates the conditions for interference to occur over a wide area.
So diffraction is the spreading, and interference is what happens when those spread out waves meet and combine.
That's a great way to think about it. Diffraction gets the waves to the same place, and interference describes the result of their meeting them, the constructive and destructive addition. The patterns you see from slits or gratings are fundamentally interference patterns enabled by diffraction.
Got it. Diffraction bends, interference combines.
You could say that, and we see the results everywhere.
Like those beautiful shimmering colors on a soap bubble or an oil slick? You said that's interference.
Absolutely. Thin film interference. It's a fantastic everyday example. Light reflects off the top surface of the thin film.
Like the outer surface of the soap bubble?
Right. And some light goes through, reflects off the bottom surface of the film, and comes back out.
So now you have two reflected waves coming back toward your eye.
Exactly. But the wave that reflected off the bottom surface traveled a slightly longer path down through the film and back up.
And that extra path creates a phase difference.
It does. That path difference, plus potential phase flips on reflection, means the two returning waves interfere. Depending on the film's thickness at that point and the angle you're looking from, certain wavelengths, certain colors of the incoming white light will interfere constructively.
Making them look bright.
And others will interfere destructively.
Making them disappear or look dim.
Right. So the color you see is the result of which wavelengths are being reinforced and which are being canceled out by interference. And since the film thickness varies, the colors shift and swirl.
That's brilliant. Makes sense why they look so dynamic. Okay, so we've covered water, sound, light, but the sources mention something even stranger. Quantum interference.
Yes. This is where things get really counterintuitive, even by physics standards. It turns out that matter itself, things we normally think of as particles, like electrons, atoms, even quite large molecules.
They behave like waves.
They exhibit wave-like properties. And because they have wave nature, they can interfere.
Wait, a single electron can interfere? With what?
This is the core mystery highlighted by the double-slit experiment when performed with particles. In quantum mechanics, you describe a particle, like an electron, not just by its position, but by a wave function, usually written as psi.
Okay, the wave function.
And the probability of finding that electron at a particular place is related to the square of the magnitude of that wave function at that place.
Like intensity being related to amplitude squared for light.
Exactly the same mathematical relationship, which is suggestive. Now imagine sending one electron towards a barrier with two slits. If the electron could go through slit A or slit B, its wave function becomes a superposition, a sum of the wave function for going through A and the wave function for going through B.
So A plus A.
Basically, yes. And now when you calculate the probability of finding the electron on the screen behind the slits, you have to square this sum, A plus A.
Which isn't just the sum of the squares.
Exactly. Just like with light intensity, you get A plus an extra term, the quantum interference term.
And that term depends on the phase difference between the going through A part and the going through B part of the wave function.
Precisely. So this interference term can increase the probability in some places, constructive probability interference, or decrease it even to zero in other places, destructive probability interference.
So even though you send electrons one by one,
over time, they build up an interference pattern on the screen. Bands where they land frequently and bands where they almost never land.
That's deeply weird. It's like the single electron goes through both slits simultaneously and interferes with itself.
That's the standard interpretation, as strange as it sounds. The source quotes Dirac saying every photon interferes with itself. And the same applies to electrons. Feynman famously said the double-slit experiment with electrons has in it the heart of quantum mechanics. In reality, contains the only mystery.
Wow. So interference isn't just a wave thing. It's fundamental to how reality itself works at the smallest scale.
It seems to be, yes. It forces us away from simple particle pictures.
Okay, mind sufficiently bent. But these phenomena, interference and diffraction, they also have very practical uses, don't they?
Oh, absolutely. They're not just theoretical curiosities. They're the basis for many important technologies and measurement techniques.
Like beats in sound.
Yes, beats are a direct result of interference between two sound waves that have slightly different frequencies.
So when you hear that wah 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 sound when two notes are almost in tune.
That's it exactly.
Mm.
As the two waves drift in and out of phase because of their slight frequency difference, they alternate between constructive interference, making the sound louder, and destructive interference, making it quieter.
And the speed of the wah wah tells you how far apart the frequencies are.
Precisely. The beat frequency is the difference between the two sound frequencies. So musicians use it to tune instruments you adjust until the beats slow down and disappear, meaning the frequencies match.
Clever. Okay, what else? The general term is interferometry, right? Using interference to measure things.
Yes, and it's incredibly powerful. Optical interferometry using light was fundamental in establishing the wave nature of light with Young's experiment back in the early 1800s.
And later, the Michelson-Morley experiment used it to test for the luminiferous ether.
And its null result was a crucial step towards Einstein's theory of relativity. It showed something profound about space, time, and light.
And we still use optical interferometry today for super precise measurements.
Absolutely. In metrology, the science of measurement, it's used to define and calibrate length standards. For instance, the meter was once officially defined based on the wavelength of light from a specific isotope of krypton, measured with interferometry.
Wow.
And it's still used to calibrate things like gauge clocks, check the precision of machine tools, and test the shape and quality of lenses and mirrors. It allows for measurements down to fractions of a wavelength of light.
So incredibly precise length measurement. What about other kinds of waves? Radio waves.
Yes, radio interferometry is huge in astronomy. Instead of building one impractically enormous radio telescope dish.
You use lots of smaller ones spread out.
Exactly. An array of radio telescopes, like the Very Large Array, VLA, in New Mexico, they combine the signals received by each individual dish.
How does interference help there?
By carefully measuring the arrival times or phases of the radio waves from a cosmic source at each separate dish, computers can combine the signals using a technique called aperture synthesis. The interference patterns formed by combining these signals allow the array to achieve the same resolving power, the ability to see fine detail as a single giant telescope with a diameter equal to the largest separation between the dishes in the array.
So they synthesize a virtual telescope that's miles across.
Effectively, yes. It lets astronomers map distant galaxies, star-forming regions, and other cosmic objects with incredible detail.
Amazing. So tiny links on Earth, vast structures in space, any other types.
The source also mentions acoustic interferometry.
Using sound interference for measurement.
Right. It's an instrument used to measure properties of sound waves, like their speed or wavelength within a medium, often a liquid or gas. You set up standing waves, which are themselves an interference pattern, and analyze them.
Okay, so it really is everywhere. Tuning forks, bubbles, quantum physics, astronomy, precision engineering.
Interference and diffraction are fundamental concepts that pop up all over science and technology. They reveal deep truths about waves, light, and matter, and give us powerful tools.
It really makes you think. These interactions, which seem so strange compared to how, billiard balls bounce off each other, are actually governing so much, from the color of a butterfly's wing, perhaps, to the structure of atoms, to how we see the universe. It makes you wonder, doesn't it? What other subtle wave behaviors are shaping our reality in ways we haven't even fully grasped yet?
It's a constant source of discovery.
Thanks for listening. Write us your opinion on which application of interference you find most surprising in the comments. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.